Today we'll be talking about an extraordinary finding related to neutrinos. For the first time, the IceCube Neutrino Observatory allowed astronomers to obtain an image of the Milky Way using these tiny messengers. The image was recently published in Science, and it shows that our galaxy produces an emission of high-energy neutrinos. To find out more, we are with Sarah Mancina, researcher at the Department of Physics and Astronomy of the University of Padova, who participated in the discovery. So, first of all, Sarah, congratulations. And IceCube is a collaboration of hundreds of scientists from more than 50 institutions and 14 countries. So, would you tell us a bit more about this collaboration and also about the instrument?
Yeah, so IceCube is a collaboration of many different institutions across several continents, including Antarctica, which is where the experiment is located. It's located deep in the Antarctic ice at the South Pole. We've essentially drilled an array of very sensitive cameras. We look for charged particles, which are energetic, which as they pass through the ice, they deposit light, and this array of very sensitive cameras can pick up just a single photon, but hopefully these charged particles deposit many photons that we can use to understand the type of particle that we're seeing.
And what are the benefits of observing with neutrinos?
Obviously, astronomy first started with light because that's what we use to see. And here at Padova, obviously, they were looking at our local solar system back 800 years ago to understand the Earth, our universe. But now we've looked at all different wavelengths of light at different energies. So one section of light might be what we call the visible. We can see visible light, so that's what we see with our eyes, but then there's also many different wavelengths or energy of light that we can look at. At the highest energies, we have what are called gamma rays. And so we're trying to understand what's happening in the high energy universe. And these gamma rays are a very useful tool, but unfortunately, there's some drawbacks to using them in that as they travel through our universe, there's a chance that they may be they might interact with background light in the universe. So the further away an object is, the more likely these gamma rays might be, the word we use is attenuated. So it's sort of, they interact with the light and they disappear. We don't see them at Earth. Whereas neutrinos, they don't like to interact. So they can travel straight to us, and the odds of them interacting before they get to us are very low. So the signal is still there when it reaches Earth after traveling vast distances across the universe. However, because they don't like to interact, that makes it very hard for us to see them. So they only interact through what's called the weak force. But everything we use to observe our universe and our Earth is using the electromagnetic force. So these neutrinos, we have to hope that they interact through this weak force. And then that produces charged particles, which we can then see with IceCube. So we're looking for a signal that a neutrino was there, instead of a signal that we can't directly observe the neutrinos. We have to wait for the signal to come there. And one of the goals of this is to understand where the cosmic rays that we see at our Earth are coming from. And these high energy cosmic rays, we've tried to look to where they come from, but they're charged particles, and there's lots of magnetic fields throughout our universe. So these charged particles, the cosmic rays, their paths get bent. when they come to Earth. So we can't use them to point back. So we either have to use gamma rays or neutrinos to understand where the cosmic rays are coming from. And so, yeah, like I said, the gamma rays have the con that they can be absorbed by other matter and materials in our universe, whereas the neutrinos are less likely to be absorbed.
And how did you manage to overcome the main challenges and difficulties, such as the noises?
Yeah, so like I said, yeah, we're trying to figure out where these cosmic rays come from, but they produce one of the biggest backgrounds that we see. So they basically, the cosmic rays come in and they hit atmospheric particles, so like the air above us. And this creates a shower of particles, including neutrinos and also what we call muon, which is like a heavier electron. And the muons, those are charged particles, so they do come into IceCube, and we do see them a lot more frequently than we see neutrinos. But the muons, since they are charged particles, they are losing energy as they travel. So one thing we've done in the past is, so IceCube's located at the South Pole. We look for particles that come through the Earth. So they've traveled very far distances through the Earth before they reached our IceCube detector. And this removes the muons, which if they come from the southern sky, they can enter into our detector because it's only a short distance. But coming from the north, they get absorbed into the Earth before they ever reach IceCube. However, our galaxy, which is what this discovery is about, a lot of the most sort of dense regions of the galaxy, including the galactic center, are in the southern sky. Relative to the Earth. So what I was doing and what my collaborators who published this result were doing is trying to improve our understanding of the southern sky with IceCube. So my work, we looked for what are called starting tracks. And so this was a tool to distinguish muons from neutrinos. And so what the muons, since they're charged, they will deposit light as they enter into the IceCube detector and as they travel through it. So we'll see sort of a path of light appear in the detector. But the neutrino, when the neutrino enters, it's not depositing light because it's not a charged particle. But there's a probability it will interact inside of the detector, and then it will produce possibly a muon, which comes out. So it basically looks like you have a muon that suddenly starts inside of the detector. So that's why we call it a starting track. And so that in that way we can distinguish neutrinos from cosmic ray muons, because the muons enter in, versus the starting track, you spontaneously see a muon appear. And then my collaborators, what they did is they looked for what we call cascade events. So like I said, we can't see the neutrinos themselves, but we can sort of see the patterns they leave in our detector as a signature that there was a muon there. And these signatures can tell us different things about the neutrinos that were there. So it's sort of like the analogy we use is footprints in the snow. So you don't see the animal that makes the footprints. You just see the footprint that was left there, and you know there was an animal there. So we see the footprint left by the neutrino interaction. But neutrinos, there's 3 different types of neutrinos. We call them flavors. The ones that produce these muon tracks, we call them muon neutrinos. But there's 2 other types called electron and tau, which are related to electrons, and then also the tau lepton, which is electrons, muons, and taus are all part of the same family of particles. and the neutrinos are sort of the cousins of these particles. So getting back to the footprint analogy, a muon leaves a certain signature. So it's sort of like, oh, you say hoof prints, so maybe you know a deer came through. But then the electrons and tau neutrinos might produce what we call a cascade. So maybe you see a paw print from a cat or something. So it's sort of telling us, oh, there was a different flavor of neutrino which came in. And the advantage of these electron and tau cascade events is that they look very different from the cosmic ray muons. So that background. So the cosmic ray muons, they produce a track, and the muon neutrinos also produce a track. And it's hard to distinguish between them, but we do have tools to do that. But with these cascade events, it looks very different. And so what happens is essentially the particles which are produced, they kind of bounce around instead of traveling in a straight path. And in the detector, it looks like you see this bubbling out of light out of a point. What's great about that is it looks very different, so it's easier to distinguish it from the background. The hard part is because your particle starts bouncing around, it's hard to tell the initial direction of the particle. So it's hard to point back to where the particle came from. But our collaborators who wrote this paper developed a new neural network tool to reconstruct the direction of these cascades. And that allowed them to get a better understanding of the direction of the cascade events, which allowed them to point back to where the neutrinos came from. And then they found an excess of these neutrinos coming from the direction of our galactic plane.
What are the main implications of this observation, I mean, in our knowledge of our universe?
We've looked at our galaxy in many different wavelengths of light. And so this is the first time we're looking at our galaxy in in the neutrino sky. So this is our first glimpse of what our galaxy looks like. And you can see in the picture that it's maybe a bit less resolved, a bit less clear than the other wavelengths of light. And that's because this is a developing technology. So in the future, we're working on getting a clearer image of what we're seeing, what the galaxy looks like to us in neutrinos. But yeah, so this can help us understand better about how neutrinos are produced within our galaxy and within the universe in general, and what sorts of objects are creating cosmic rays or neutrinos. This discovery, so seeing neutrinos from our galactic plane, it's something we expected to see because we see cosmic rays at Earth. They're interacting in our atmosphere. We know these cosmic rays are existing elsewhere in our galaxy, we would hope. And so we expected to see that same sort of gas of cosmic rays that interacts with our atmosphere. We would expect to see that interacting with the gas that exists within our own galaxy, our own nearby Milky Way galaxy. And so that's what we think is producing the signal of neutrino is the same cosmic rays that interact in our atmosphere are also going through and interacting with the galactic plane.
And what are the next steps for this line of research?
The next steps are we're still continuing to try to understand where all of our neutrinos come from. We know we see, we've proven that we see an astrophysical flux of neutrinos. We know that part of this astrophysical neutrino signal is coming from the galactic plane now, but we know that it's also possibly coming from extragalactic sources. So we're trying to understand what sources outside of our galaxy are producing the neutrinos, but also within our own galactic plane, understanding exactly what we're seeing within this neutrino sky. So resolving better the shape of the neutrinos that come from our galactic plane will be of importance. It can help us understand how much of it is, like I said, just this sort of diffuse cosmic ray flux that's permeating throughout our galaxy and interacting with the gas, versus potentially sources of cosmic rays and neutrinos that are actually active within our galaxy. So things like a supernova remnant, where you have a star that's exploded and there's hot plasma and things like that, which might be creating the cosmic rays and neutrinos, versus, like I said, just overall sort of things just interacting with the galactic plane medium.
A last question, more personal. What is the most exciting aspect of your work?
I guess it's just fascinating to understand what's happening in our universe. It's exciting to see that we're resolving the neutrino sky. So we have all these pictures of what our universe looks like in different wavelengths of light, and now we're adding on a new particle where we can create a map of our universe in neutrinos. And we're really at the beginning stages of it. It's, I guess, yeah, for me, I like, part of what I like too about neutrinos is they travel at the speed of light. And so that means they can sometimes come from very far away and a very long time ago. And so in some ways, we're understanding what was happening in our universe hundreds, billions of years ago. So for me, it's sort of like universe history, which I think is interesting to know what was happening before we got to where we are in the universe.